You all welcome Professor Eric Smith.
Thank you. I have to say, if I didn't have obligations on this Sunday, I think I'd go see Michael Kona. As he said, today I'm here to talk about the idea of the fine-tuning of the universe. And historically, this has been referred to as the teleological argument. And that's simply an argument for God's existence through design, through the fact that the universe does not appear to be random, that it has been specifically designed for human habitation, for human support. And the word telos there in the Greek means end or purpose or goal. So the idea is that God designed the universe with a purpose. Its purpose is evident through its design. And the designer itself is evident beyond that. Now, obviously there's been a lot of work done on the idea of fine-tuning of the universe for life recently, but this is probably the oldest branch of apologetics in existence. It goes all the way back to the Bible. Psalm 19:1, which most of you are probably familiar with, the heavens declare the glory of God, the sky displays his handiwork. And Romans 1:20, since the creation of the world's invisible attributes, his eternal power and divine nature have been clearly seen because they are understood through what has been made. So people are without excuse. So that's what we're here to talk about today. What can we see in the universe by looking at it that gives evidence that God is there? And you don't even have to go to Christian sources for this. Aristotle and Plato actually had a lot to say about it themselves. I won't read the quote, but basically Aristotle's gist here is that even if people knew nothing about religion or nothing about gods, that they could look at the earth and come to a conclusion that these works were the handiwork of divine beings, that they couldn't have come about through chance. And probably the best known version of this argument is by a man named William Paley. It's known as the watchmaker argument. Basically, the idea is that if you were out walking and found a watch lying on the ground, just by looking at that watch, you could tell that it had been designed, that it wasn't a random occurrence, that the watch itself bare hallmarks of its designer. And while this has been an argument that's fallen sort of in and out of favor over the years, I think it still does a very good job of putting forth a good picture of what we're looking at, even if there are points that philosophers might disagree with. Now, this whole idea of the universe being designed, of it appearing to be very specifically made for life, isn't something you even see among theists. A lot of scientists nowadays, atheist scientists or agnostic scientists, comment on this same thing. I have this in a different order. So, Fred Hoyle states that a common sense interpretation of the facts suggests that a super intellect has monkeyed with physics, as well as with chemistry and biology, and that there are no blind forces worth speaking about in nature. Paul Davies, who is an atheist scientist, stated that there is, for me, powerful evidence that there is something going on behind it all. It seems as though someone has fine-tuned nature's numbers to make the universe, and the impression of design is overwhelming. And finally, Roger Penrose, an Oxford mathematician and physicist, friend of Stephen Hawking, stated, I would say the universe has a purpose. It's not just there somehow by chance. None of these are Christians, none of these particularly theistic scientists, but they all recognize that the universe has at least some appearance of design. It looks non-random. And to us, this is a clear indication that the universe isn't random, that the appearance of design is actually design. And so the general form of this teleological argument goes like this, and somehow my slides got out of order. But the first statement, going to sort of a three-statement typical philosophical format, says, if the universe is fine-tuned for life, it must be either through necessity, chance, or design. There really are no other options. It's either that way because it has to be, it's either that way because we looked up, or it's that way because it was made to be that way. Secondly, the fine-tuning is not through necessity or chance, which I hope to give some evidence for today. So if that is true, therefore, it must be by design. So today I'm going to really be looking a lot at these first 2 points I'll talk a bit about some of the evidences we see for fine-tuning. What indications are there that the universe was in fact made for human life? And then I'll go through some of the arguments for necessity or chance and see how they do seem to come up short. Which again, if it's neither necessity or chance, that leaves only the possibility of design. So first, is the universe fine-tuned? I have to say, if you're not a science person, you're going to get some physics in here today. But I'll keep it fairly basic. So we'll look at some of the basic forces, some of the constants, some of the components of the universe, all which appear to be very fine-tuned. And by fine-tuned, I mean that they are restricted to very narrow possible quantities. That these forces like gravity, for example, couldn't just have been anything. That for the universe to support life, there's only a very narrow range they could have. So first of all, gravity. There are lots of things that are fine-tuned about gravity. For one thing, if gravity were about 3,000 times larger, life really could not exist. Not on Earth, not really on any planet. It would just be crushed. Now, 3,000 seems like a lot. That doesn't sound very fine-tuned. If the gravity could be up to 3,000 times more. But in order to really get perspective here, you have to look at the range that gravity could have. Now, there's no way we can say the total range of strength that different forces can have, but the most powerful force in the universe, which is the strong nuclear force, is about 10 to the 40 times more powerful than gravity. That's a 1 with 40 zeros after it. And so we can take that as a general range for the forces. Gravity is the weakest force. The strongest force is 10 to the 40 times stronger. So if that's the range that gravity could have had, how does 3,000 times compare to that? So comparing that, 3,000 to 10 to the 40 means that gravity is tuned to 1 part in 3 to 10 to the 37. So that's a 1 with 37 zeros after it. So that's saying that gravity could only be off by that amount for life to still exist. And that's a very, very, very narrow range. So if gravity could potentially be all the way up to 10 to the 40 times more powerful, but only 3,000 times more powerful would make life impossible, then gravity is very finely tuned. It is inhabiting a very narrow range that lets life exist. Other fine-tuning components of gravity. If gravity were too large, stars would burn rapidly and unevenly. Gravity is really what drives stars burning their fuel. It forces the stars to contract. That heats them up. That heating allows the stars to burn hydrogen, and that's what creates their energy. If gravity were a little bit stronger than it was, stars would burn much faster. And when stars burn that fast, they burn very unevenly. They become very unstable. An unstable star would not allow life on Earth. It would simply scorches at times, freezes at others. Too small, however, and stars cannot burn heavy elements. In the Big Bang, the only elements created were hydrogen and helium. Maybe a little bit of lithium. Every other element in the universe, all the iron in our blood, the carbon in our bodies, the oxygen we breathe, those are all created inside stars. But if gravity were just a little bit weaker than it is, stars would not be able to create those elements. And we'd end up with a universe of nothing but hydrogen and helium, with maybe a little bit of something like carbon. But that would be it, and life could not exist. So gravity has to inhabit this very narrow range for life to exist. It has to be enough to allow stars to burn, but not so much that they burn out quickly or burn unevenly. And there are other aspects to gravity as well. We'll see as we talk about other things. But gravity is certainly one force that, even though it could have had a wide range of values, a wide range of strengths, in order to allow a universe where life could exist, could only have one very specific, narrow range of values, which it happens to have. The next is what's known as the strong nuclear force, which, as I said, is the strongest force in the universe. universe. Now, the strong nuclear force is what holds atoms together. If you're familiar with the idea of how an atom is constructed, the nucleus, the center part of an atom, is made up of protons and neutrons. Neutrons are neutral, protons are positively charged, and positive charges want to push away from each other. So the nucleus of an atom should fly apart because you have all these positive charges there and they all want to push away. It's this strong nuclear force that overcomes that to hold the atom together. And this is, at short distances, the strongest force in the universe. As I said, it is 10 to the 40, 1 with 40 zeros after it, times stronger than gravity. So, holds atomic nuclei together. Only works over short distances, however, which is why most people aren't familiar with it. It's a nuclear force, only works in the nucleus of atoms. If it were 0.5% stronger, not 5%, not 50, 0.5% stronger, there would have been no hydrogen left after the Big Bang. The Big Bang goes off, hydrogen begins to form. But if the strong nuclear force was much more powerful than it was, that hydrogen would very quickly start to fuse into heavier elements. And we'd be left with no hydrogen. But no hydrogen means no water, for one thing, if nothing else. And no acids, no bases. Almost everything in the universe depends on hydrogen in some way. But if this force were only 0.5% stronger than it was, you would not have that hydrogen. You would have a universe completely incapable of supporting life. It also would even be much more difficult for stars to exist because stars use hydrogen as their fuel. 0.5% weaker than it is, you would get only hydrogen in the Big Bang. No helium, nothing else, and you did it with a universe that was too light, where those elements where that precisely balanced ratio of hydrogen and helium didn't exist. And you did it with a universe where you didn't have stars and galaxies. It would just be nothing but hydrogen gas. So again, very narrow range. 0.5% too much, 0.5% too little. You get a universe that's basically nothing. On the other end, we have what's known as the weak nuclear force. The weak nuclear force is kind of confusing. It's hard to describe. Basically, the weak nuclear force is active in radioactive decay. It allows elements to change into other elements. And I'm not going to go into a lot of detail on it. That's, a lot to go into. But in terms of fine-tuning, okay, for our purposes, we can just know that the weak nuclear force transforms protons into neutrons, electrons, and into neutrinos. That's what creates radioactive decay. If it's too strong, then too much hydrogen converts into helium with the Big Bang. So you get something similar to before. You have too much of this, too much hydrogen changes into helium, you're left with a universe of little to no hydrogen. And too weak, once again you have little helium created. So both these strong and weak nuclear forces had to be very precisely balanced. Or you get a universe that really doesn't go beyond those early stages. There's no hydrogen or no helium. The universe doesn't really evolve into something life-supporting, or even planet-supporting for that matter. Speed of light. Now the speed of light is an independent constant. It actually depends on electric and magnetic forces. But it turns out, and this is a fairly recent discovery, some of the people have been working on within just the last few years, and that these electric and magnetic forces that go into creating the speed of light regulate quantum mechanical effects. And our bodies depend on quantum mechanical effects, not to mention all our technology. So if these quantum mechanical effects, things like tunneling that I won't go into because I don't want to get too technical, if they were stronger or weaker than they were, then our bodies could not operate. And our technology could not operate. So even slightly varying the speed of light would destroy that. Which is why I find it amusing that some scientists like to speculate at varying speed of light, but physically that's impossible. Another aspect, quarks. So first, what is a quark? More than just a Ferengi from Deep Space Nine. Quarks are what make up protons and neutrons. A lot of people, are taught that your three basic components of an atom: a proton, a neutron, and an electron, and that's as small as you can get. Everything stops there, and that's not actually true. In nature, you don't get any smaller than that. Protons and neutrons stay together, but you can break them up more, and then you get these objects called quarks. And there's actually 6 different kinds. There's an up quark, a down quark, a strange quark, charm, top and bottom. Names, by the way, are purely random. There's something particularly strange about the strange quark or charming about the charm quark. They just had to come up with names to describe their different properties. But these are the objects that make up protons and neutrons, and thereby make up atoms. And they make up a bunch of other more bizarre particles as well. But the interesting thing here, and this again is a very recent discovery, this is what is just going on recently, is that all these quarks have different masses. Up and downs have a certain mass, strange charms, and there's a fairly wide range of masses here. Some of these quarks are very heavy, some of them are very light. But their particular way their masses are arranged contributes to what's known as CP symmetry breaking. Now, what is that? To understand this, you have to go back to the Big Bang again and understand how matter came to exist to begin with. When the Big Bang goes off, you have a universe of nothing but energy. Big Bang universe is filled with nothing but energy. There's enough energy to spontaneously create matter and antimatter. But the rules of physics say that you can't just create matter and antimatter by itself. You always have to create a pair. One particle, one antiparticle. And these particles can't last very long. Or it violates what's known as the uncertainty principle. So these particles pop out of the universe in pairs, quickly annihilate themselves, and go back to being energy again. Now, if that process proceeds perfectly, symmetrically like that, then you end up with a universe that's never anything but energy. The matter that pops out quickly disappears. And so you end up with a universe of nothing, really. However, in the very, very, very early universe, you have what is called the CP symmetry breaking, which means that a little bit more matter was created than antimatter. Not much, a very, very, very small amount. But that means that when all the matter and antimatter annihilates itself, the only thing left over is matter. And it's that little tiny bit of leftover matter that creates the entire universe we see today. So all the matter out there's only a very small fraction of what was actually created. It's just most of it got turned back into energy again. And that's because of this CP symmetry breaking. Without that, we would have a universe, again, that was nothing but energy. But, again, very recent research is showing that this distribution of quark masses determines this. And if the distribution of masses among these quarks were different, if, say, some of them were slightly more massive, some of them were slightly less massive, we would not get the right amount of symmetry breaking. We'd end up with a universe with either too much matter, which would very quickly collapse back in on itself again, or a universe with not enough matter, and again, you would not be able to form stars and galaxies and planets. So, even just how these very, very tiny particles are distributed is necessary for a universe being what it is. And again, we don't know of any reason that these particles had to have the masses they do. And if they had some other kind, again, we would not have been able to have a universe at all. And I know we're getting somewhat obscure here, but there's a lot to be said for a lot of these tiny little parts of the universe no one ever thinks about. And a lot of people are just now researching them and understanding how precise they have to be to allow the universe to work, to allow everything to fit together. So the next one to look at is what's known as the fine structure constant, or alpha. You see it here. The fine structure constant basically determines how strong the electromagnetic force is. Now, the electromagnetic force is the force that holds everything in this room together. Normally, when you think of forces holding things together, people think of gravity, because it's gravity that holds us to the Earth, it's gravity that holds the Earth together as an object, it's gravity that holds us in orbit around the sun. But we don't have enough gravity in our own bodies to hold us together. And so everything we see here is actually being held together by electromagnetic forces. Protons and electrons attracting each other. And this fine structure constant determines how strong it is. And the 1 over 137 here means that it's 1 over 137 times as strong as the strong nuclear force. This is comparing it to that strongest force. So it's 137 times weaker than our strongest force, which still means it's very, very, very strong. Remember, gravity is 10 to the 40 times weaker. But it turns out that, again, this is a very precise number. If this were off by only 3%, then stars would not produce enough carbon. Now, the reason for this gets into something called Hoyle states, which is a very specific energy state of carbon, and allows carbon to have all the properties that it does that allows life to exist. Again, that's way more detail than I think anyone here wants me to go into. But it's determined by this fine structure constant, the strength of the electromagnetic force, and if we're off by only 3%, we would not have enough carbon produced in stars. And, of course, we are carbon-based life forms, as every Star Trek fan knows. So without this being exactly this result, exactly this value, then, again, life could not exist. Also, 6% larger. 6% larger, the electromagnetic force would be a bit stronger, which means that matter would not be able to exist inside of large magnetic fields, like, say, the one the Earth has. So this structure being a bit stronger, matter would be unstable. And magnetic fields are everywhere. They're in the Earth, they're in the sun, they're all through space. They're very common. So again, just a little bit off, and those magnetic fields would have really disrupted any matter that managed to exist, because it would have had too strong a pull on those protons and electrons in the atom. So these are some of our constants. These are the constants that describe how the universe works, to sort of show how everything fits together. There are also what you can think of as sort of initial conditions. How the universe was set up from the beginning that allowed it to exist and continue to exist. And one of those is what's known as Big Bang entropy. A word on entropy. You say entropy, what do most people think of if you think of anything? Yeah. Most people will talk about disorder. Entropy is a measure of your disorder. And that's fairly accurate. It's a good colloquial description. Technically, entropy is a number of how many possible states you can have. But disorder, there's lots of ways for things to be disordered. There's only a few ways something can be ordered. I take a bunch of things and line them up on the desk here. There's only one way or a few ways to line them up. If I just drop them and let them fall where they want to go, there's lots of ways they can be arranged. So high entropy means lots of possibilities, so a lot of disorder. Low entropy means only a few ways that things can be ordered, so a small amount of, so very, very ordered. So the entropy of the Big Bang, how ordered was the Big Bang? Well, it turns out the Big Bang, entropy had to be just right. If the entropy was too high, that would mean the Big Bang was too smooth. That when the Big Bang went off, the universe would have been too even. You would have had a universe filled with energy and matter, but it would have been spread very evenly everywhere. There wouldn't be any clumps, any places where matter was closer together than other places. And this is actually kind of what you expect. Because after all, the Big Bang came from what's called a singularity. It's matter and energy all clumped together in a dot. So when it goes off, you would expect it to go off evenly in all directions. There's no reason it shouldn't. But that's not what happened. That would have yielded high entropy. it would have been very disordered because everything was spread out. So if that had happened, we would not have any galaxies or stars because there would have been no place in the universe more likely to clump together than any other place. And so nothing would have clumped. The universe would have stayed just matter and energy evenly spread throughout. So we have to have just the right amount of clumping. Too little, you don't get stars and galaxies. Too much, and you end up with galaxies filled with nothing but black holes. So, this is the biggest number here. The odds of the Big Bang having the exact right amount of entropy to produce a universe of stars and galaxies like we see is 1 chance in 10 raised to 10 to the 123rd power. So that's a 1 followed by 1,230 zeros. This was actually calculated by Roger Penrose, that man I mentioned before, a friend of Stephen Hawking, Oxford mathematician and physicist. He was the one who calculated this. So of all the possible entropies the Big Bang could have, we ended up with the 1 in 10 to the 10 to 123rd power that would actually produce a universe of anything at all. Now this is interesting. It's actually more probable that instead of getting a real universe, we have what's called a Boltzmann grain. And a Boltzmann grain basically is the idea that there is some finite possibility, very, very unlikely, but a finite possibility, that instead of having a universe, that instead what happened was a single mind, a single brain, popped into existence for a short amount of time and thinks it sees a universe. So you could be, this Boltzmann brain that popped into existence for a brief period and is imagining everything you see and very shortly will pop back out of existence again. And that is actually mathematically more probable than getting a Big Bang that's this fine-tuned, that has this exact amount of entropy. And again, this was calculated by Roger Penrose, who's in no way a theist. But simply mathematically, the Boltzmann brain is actually more probable. It's more likely that the whole universe is an illusion than that it is this actually finely tuned. I just find the Boltzmann brain idea cool. It's the whole, philosophical argument. What if you're really a brain in a vat? I remember I was at Governor's Honors as a high school student many years ago, and a group of students got together to discuss that. Imagine a bunch of 11th and 12th graders talking about philosophy. And their conclusion was it doesn't matter. You just have to live, whether you're a brain in a vat or not. But according to this, it's actually more likely that you're a brain in some type of metaphysical vat than the universe actually exists. So another one of these initial conditions that the universe had to have right from the very beginning. And remember, everything about the universe as it is now comes from the Big Bang. It comes from those few seconds of existence that set the stage for everything else. So we see the entropy of the Big Bang had to be exactly right from the very beginning. The mass density, how much matter there was in the universe compared to its volume, had to be exactly right. Now this ties back into what we were talking about before. A lot of this stuff, ties together, which is usually the case in good physics. Your mass density has to be just right, again, to get this proper hydrogen-helium ratio. Again, if there's too much mass, then you have too much clumping, you have too much matter fusing into heavier elements. So too high, stars are too productive. They produce too much heavy elements. Stars burn too rapidly because there's just too much mass, there's too much gravity. Too low, again, stellar fusion can produce these heavy elements. So this is one way in which that mass density had to be just right from the beginning. Another, though, I think is more interesting, probably because it has more to do with my own research. If the mass density were too high, the expansion of the universe would slow down. Remember, the Big Bang goes off, everything in the universe flies away from everything else. Still flying away from everything else. If there's too much matter, though, there's too much gravity. And that slows that expansion and begins to reverse it. And the universe collapses back in on itself very quickly. It doesn't take much. Or, even if it is allowed to expand for a bit longer, you end up with nothing but black holes and neutron stars. Nothing that can support life. Too low, and the universe expands too fast, which means matter gets spread out too much, it gets spread out too evenly, stars never form. So again, to allow the exact clumping that we see in the universe. And this is a nice little three-dimensional image of how that clumping looks today. You know, all these are strings and filaments and sheets of galaxies and galaxy clusters that align themselves around that original clumping of the universe after the Big Bang. If that had not been just right, we would not have any of this. And the fine-tuning there had to be 1 part in 10 to the 60. You vary it just by that small amount either way, and you don't get a universe that allows for stars and galaxies to form. And again, it has to be this from the very beginning. These are these initial conditions the Big Bang had to have right from the start. Next, the idea of dark matter, which a lot of people hear, know the word. A lot of people don't know what it means. Dark matter is simply matter in the universe that we cannot see. Now, some of this matter is just ordinary matter. It's rocks and planets and clouds of gas and dust that just aren't bright enough for us to see them. But most of it is actually a type of matter that's completely unlike the matter that we're used to. They're what are called exotic particles, WIMPs. That's W-I-M-P, weakly interactive massive particle. But these are exotic, unusual particles created in the Big Bang that really permeate the universe. And it turns out they're actually necessary for galactic stability. When I talked here a couple years ago, I went into a lot of the requirements for the Earth and our solar system to be able to support life. And part of what I talked about was how galaxy structure has to be very stable. We live in a spiral galaxy with a very specific part of the spiral galaxy. And if that spiral galaxy isn't stable, if it isn't keeping the same shape and rotating the same way, over a long period of time, life couldn't exist. And the reason it can do that is because of dark matter. But the dark matter around the galaxies have to be arranged in just the right way. Specifically, they have to be arranged what are called halos. So if you had our galaxy, here, think of it like a plate. It's surrounded by this halo, this sphere of dark matter that we can't see. We only know it's there because we see the effect of its gravity. But it stabilizes our galaxy. Its gravity all around us helps to keep the galaxy from collapsing in on itself. That without that outward pull, galaxies would very quickly collapse in and merge into this huge clump of matter at the center of the galaxy, end up feeding the huge black hole that lies at the center of our galaxy. So again, this distribution has to be just right to prevent that. Also, we talked about the mass density before. It has to be just right. Well, it turns out that if you count up all the matter we see in our universe, that what we see isn't anywhere close to the necessary mass density. That our universe should have, basically expanded itself out of existence long ago. It turns out that it's this dark matter that makes up the rest of it. And it's by far the majority of matter in our universe, by several factors. But it's important that it be dark matter to make it up, because if the universe was filled with this bright matter, then we would never even have a nighttime. Our sky would be completely white all the time. It would be constantly glowing. So it's necessary that the majority of the matter of the universe be this dark matter that we can't see, that emits no light, but still affects us by its gravity. And again, the percentages have to be just right. a little bit off either way, and you end up with something unstable. Now, the last component is the dark energy, which again is what my research group in grad school worked with. And we have the nice little graph here showing normal matter makes up 4% of the universe. Our dark matter makes up 21%, so it's about 5 times as common. The entire rest of the universe is this dark energy. It makes up 3/4 of the universe, and we only just discovered it, about a decade, less than a decade ago. And of course, that means 96% of the universe is stuff that's completely outside of our everyday experience. But what is dark energy? I actually gave a talk in here about that a few years back, but other than Bobby, I don't know if anyone else was here for that, because I think everyone's changed over. But brief synopsis of that, dark energy is this energy that's part of space itself. And it's actually pushing outward. Everyone always knew the universe was expanding. We've known that ever since the beginning of the 20th century. We know that everything in the universe is moving away from everything else. But we expected that to be slowing down. Because there's still gravity, there's still matter. Even if it's moving outward, gravity should be putting the brakes on. So what the head of my research group wanted to do when he first started his project was to try to get a measurement of exactly how fast the universe was slowing down. And by doing that, be able to determine exactly what would happen to the universe at the end. Would it keep expanding, just moving slower and slower? Would it recollapse? And what he found was what no one had really expected. And that is, the universe wasn't just expanding, but it was speeding up. And it's this dark energy that's, we believe, to be the cause of that. It's this energy in space itself that is pushing outward and making the universe speed up, move out faster and faster and faster. And it's this dark energy that makes up most of the universe. Now, in order to allow the universe to exist, at the very beginning, at the time of the Big Bang, the dark energy had to be tuned to 1 part in 10 to the 120. So that's a 1 with 120 zeros after it. So it had to be tuned to that amount of precision. If it were even a little bit off to either way, you either have a universe that again collapsed back in on itself very rapidly, or flew apart so fast that nothing could form. So, as I said, without this fine-tuning, the universe either flies apart or collapses. Another important thing is that this gives us the last final piece of the puzzle in terms of the density of the universe. We talked about mass density before, but some of you at least are probably familiar with the whole E equals mc squared. Energy and matter are the same thing. And so this dark energy contributes to the mass density of the universe, just like the dark matter and regular matter does. And it rounds out to give us the exact right number to have a flat universe. And again, this has to be very, very precisely tuned. A little bit either way, and we'd have a universe that was too curved one way or another. So again, all of this fits together to give us the kind of universe that allows for life to exist, that allows stars and galaxies, and even allows the universe to exist, period. If things like dark energy or the mass density were off by a little bit from the very beginning, we might have had a universe that completely collapsed back in on itself a fraction of a second after the Big Bang. But because these values are exactly what they are, it continued.
Eric, can I just throw out one analogy? Just
Yeah.
say that 120. That's a big number. And what I was told was, if you cover the entire North American continent with dimes and stacked it all the way to the moon, and you had 1 billion of those continents, and you put one red dime in there, that one red dime would represent the 1 part of 10 to the 120.
Yeah, and it had to hit that number exactly.
So that when you're talking about the 10 to 120, one red dime, 1 billion continents stacked with dimes all the way to the moon, very, very small number. I mean,
And even the mass density at 10 to the 60th, actually read a good analogy for that. And basically the analogy for there was that, imagine say like an aircraft carrier that's coated in paint. You take a single fleck of paint the size of a dime off that aircraft carrier, that's the amount of shift in mass proportionally that we're talking about with the mass density. So that little fleck of paint to the mass of the entire aircraft carrier. That much off either way. And you'd end up with a universe incapable of supporting life. So yeah, these numbers really just go completely outside of human comprehension. We can really only deal with them on paper. But the mathematics, are fairly clear when it comes to them. So that's our fine-tuning. And again, there's no real debate on any of the physics I've given you so far. It is what it is. The debate comes in the interpretation, of course. Is this enough to allow a conclusion for a designer, or could this have happened due to chance or by some physical necessity? So let's take a look at some of the arguments about that. Okay. So first, let's look at the idea of necessity. And by necessity, I mean, do the physical laws of the universe require these constants to be what they are? Did they determine the constants? Are the constants these values because the laws of the universe say they have to be? Well, currently, there is no known physical law that requires the constants or these initial conditions to be what they are. As far as we can tell, the forces of the universe could have had any strength they wanted. And these initial conditions could have been anything. So constants appear to be arbitrary. In physics and mathematics, they're what are known as boundary conditions. They're just the values that you're given at the start that you have to work with. They're not necessary values. And as an example, to show this, in theory, which to me is, and a lot of people think is somewhat questionable, but it's a good example. In theory predicts a possible 10 to the 500 possible universes. Now that doesn't mean that there are 10 to the 500 universes. That means that if you take the equations of in theory, there are 10 to the 500 possible solutions to them that can describe a universe. And there's no reason, again, from what we know of physical law, to pick one universe over another. So there are 10 to the 500 possible combinations of values for all these constants. And we end up with the one that works. So there seems to be no reason to think that there's a physical necessity for these constants, that they had to be what they were because the laws of physics require them to be. They appear, as far as we can tell, to be perfectly arbitrary. So what about chance? There are lots of sort of different chance-based arguments. How, we could have just sort of lucked up. One that I saw by doing some of the research of this talk was that some people suggest that lack of tuning in one constant can be made up by another. That maybe it's not that these constants are fine-tuned, it's just that where one falls short, another can step in, and they all sort of work together. I see a few problems with this. One is that really just shifts the tuning from one thing to another. It doesn't get rid of it completely. All it's saying, well, this constant isn't fine-tuned at all, so this one has to be fine-tuned to take it to compensate. So that just kind of shifts it over. So now you have multiple tuned constants, which doesn't seem to help at all. So I don't see this argument really, holding a lot of water. Not to mention the fact that some of these constants can, compensate for another, but some of them don't really have the same effect as others. For instance, the changes in the mass density aren't going to make up for deficits in the strong nuclear force or gravity. There's just too much difference between them. So this argument to me doesn't seem to say much. I think that's Victor Stenger's argument, by the way, if people are familiar with him. Another thing that people bring up, if there are different constants, maybe we just have different kinds of life. we wouldn't have humans, but maybe we'd have, starfish aliens or giant squid or something. Or energy beings, they'd all be a cube. The thing is that, as far as we know, for any type of life that we're familiar with, that all life has to meet certain basic requirements to be called life. Life has to be able to take in energy and convert it, and to reproduce, and to do all these other things that allow it to be called life. So no matter what the form, life has certain requirements. And changing these constants would not allow for those requirements. So fine-tuning seems to be necessary for all of life processes, which isn't surprising because life processes are very delicate, they're very specific.
And I did visit Star Trek Q. I don't think he had enough. I don't believe he was on enough episodes. I'm just saying. I'm just saying.
Too much of a good thing for that.
Yeah.
Well, I don't know. Hey, I don't know.
Would I reveal my misspent youth if I say read some of the novels? And furthermore, there's no evidence for any other type of life. Now, admittedly, if we had life that depended on completely different constants, we wouldn't see it. But so far as we know, life can only exist as life as we know it. Anything beyond that goes into pure speculation, which can be fun, but certainly couldn't be called science. So could different laws of nature allow for different constants? If the law of gravity worked differently, could we have a different constant? Well, there's just no way to answer that. I'm sure you could think up, some random equation that would work with a different constant, but that doesn't mean anything. It's completely unscientific speculation. So there's no way to know what different physical laws might be like. We have to work with the laws that we have. We don't know if other laws are possible. If they are, we don't know what they could possibly be. So this is pure speculation, which, like I say, is fun, but shouldn't really be part of the scientific discussion. Okay, now we're getting into what seem to be more meaty arguments. So this one we just looked up. The classic way this argument is usually expressed is someone has to win the lottery. It's obviously insanely improbable that any given person will win. If you win, you might have a 1 in however many million chance of winning. So your chance of winning is really unlikely. But someone has to win. So maybe we just won the lottery. But that's a bad analogy. A better analogy would be to say, imagine having one of those lottery ball spinners that was truly gigantic and can hold billions and billions and billions of those little balls. And of all those balls, they're all white except for one black ball. And you spin the wheel, and out comes the one black ball. And how insanely unlikely would that be? It would be much easier to believe the lottery was fixed than you got the one black ball out of the billions and billions and billions of white ones. And that's a better analogy because if you think about it, the first one is assuming that each, you have all these people representing, a different possibility. But as far as we know, there's only one universe. I'll get to the topic of the multiverse later. But if there's only one universe, you only have one chance. So if there's only one chance of picking the billions and billions and billions and billions of odds out, then it's highly unlikely that you're going to get it. So each ball here is equally improbable, but it's just vastly more probable to pick white than black. It is vastly, vastly, vastly more probable to pick randomly a universe that cannot support life or cannot even exist, as opposed to one that can. And mathematically, there comes a point where you go from improbable to simply impossible. And this goes well beyond that point. Another one that comes up a lot is what's known as the entropic principle. Now, the entropic principle itself is very sound and very valid. It simply says that if the universe were not life permitting, we would not be here to observe it. So of course we see a universe that allows life. It's not fine-tuning. If the universe weren't this way, we wouldn't be here and it wouldn't matter. So on the surface, and as I said, that's a valid physical principle in some way. Basically, the way physics and other sciences will use this is to say that you can only assume possibilities that allow for life to exist. That it's pointless to consider a possible solution that would not allow for life, because we know it can't be true. That's the sort of standard entropic principle. But sometimes it gets generalized out as an objection to saying that, you know, if the universe did not exist, the universe did not allow for life, we wouldn't be here anyway. So we're making a big deal out of something that had to be that way. Douglas Adams kind of put it this way. He compared it to a water puddle, saying, "Oh, look at how wonderfully this hole I'm in is shaped for me." When of course it's really the water that's shaped by the hole. That was how he expressed it. But again, this is not a good analogy. A better way to think of this is this firing squad analogy. Imagine that you're standing, in front of a firing squad, and you've got maybe 100 people that have their guns ready to shoot at you. They shoot and they all miss. Now, you could say, when the guy is surprised by that, well, of course they all missed. If they hadn't all missed, you wouldn't be here to complain about it. But it does nothing to alleviate the fact that they all missed. And that is far, far more likely that they all intended to miss than they all just happened to miss. So the entropic principle sounds good on the surface, but it does nothing to actually address the issue. It doesn't matter that we see the universe because it's light permitting. That does nothing to explain why it's light permitting. Because it's still a question that needs to be answered. It's still, the 100-person firing squad all missing. And yes, I got that one from Bill Craig's book. Anyone recognize it? I think it's a good analogy. So, the big one. The one that always comes up that everybody likes to talk about, the multiverse. Basically, there's an infinite number of universes. We are not the only one. That our universe is really just part of an enormous collection of universes, all sort of like bubbles. And they're popping up constantly all the time, and that there's an infinite number of them, and they all have different constants. They're all one of those 10 to the 500 possible solutions to M theory. Well, if you have an infinite number of universes with random constants, it is inevitable that you will eventually have one that permits life. And as I said, this is currently the most popular objection, largely because of string theory and M theory, which can allow for multiple universes. Now, that doesn't mean much. String theory and M theory basically allow for everything. But still, it's a popular objection right now. Probably because a lot of them, and this is something that people like Paul Davies, the physicist I quoted earlier, have admitted that it's basically either this or God. If you accept the fine-tuning, which is fairly well accepted, that you either have a multiverse, which makes it inevitable, or you have a God that created it. But there are some problems with it. For one thing, a multiverse generating mechanism would probably also require some fine-tuning. It would have to have a beginning, for reasons we'll get to in a bit. And in order to constantly pop out universes, there could very well be some fine-tuning required. Now, what a multiverse generating mechanism might look like is kind of fuzzy, so it's hard to say exactly what it would be. But there are other problems with it as well. As I mentioned, the multiverse would also have to have a beginning. And that's been shown through work by some different people. Basically, a lot of it has to do with the idea of entropy again. That entropy always continues to increase, and therefore nothing can exist for an infinite past amount of time. So if if a multiverse generator has to have a beginning, that means it only has a finite amount of time to produce a finite amount of universes. You couldn't produce an infinite number of universes in a finite amount of time. So once you take the infinities away, even with a multiverse, the odds of coming up with the just right universe plummet drastically. And A big problem with this is simply that a physical infinity cannot exist. Infinity is great for conceptualizing. It's great for mathematics. It's great for taking your arguments to the extreme to see how they would work out. But they can't exist in reality. You cannot have an infinite amount of time, because you simply can't count to infinity. No matter how long you count, you're always just counting one every time. You can never, there's no jump from a countable number or something to an infinite amount of something, because infinity is a pure concept. And Hilbert, the mathematician who probably did more work with the idea of infinity than anyone else in the 20th century, came right out and said that infinity is a great idea, it cannot exist in reality. You can't have an infinite regressive events. You can't have an infinite amount of past time, because you can never reach the present time. Because you can never count through infinity. So if there's an infinite amount of time in the past, how can we ever reach where we are today? Because no matter how far you counted back in the past, you still have to count further back. So even if there is this machine out there popping out universes, it does not have an infinite amount of time in which to do it. So it cannot produce an infinite number of universes. And finally, there's no evidence for such a multiverse. Certain theories allow for it, but there's no physical evidence for it. There could be no physical evidence for it by definition. Our universe is everything that we can possibly measure and observe scientifically, by definition. So anything outside of that is completely outside of our ken. We cannot know it. So we can never really have good, solid evidence for it. And so the multiverse right now is a fun idea, but it might very well never go beyond just a fun idea. Finally, one of the sort of the last objection we'll look at, and this is when they start to get kind of desperate, is the classic question, well, if someone designed the universe, who designed the designer? Almost always said in a kind of snotty tone. I found anyway. Now, there are some problems with this. For one thing, you don't need an explanation of the explanation to know which explanation is best. Think about, you're digging in your yard and you find an arrowhead. Something that's obviously an arrowhead. Well, you don't need an explanation of who created the arrowhead to know that it's an arrowhead. You don't need an explanation for the designer to know that it has been designed. The properties of the arrowhead itself tell you that it's been designed. It'd be great to know about the designer, but you don't need an explanation for his existence to know he exists. Furthermore, continuing this question would simply lead to an infinite regress. Well, who designed the designer? Well, who designed him? Who designed him? Who designed blah, 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 and ad infinitum. Ultimately, and this is the reason why, even going back to people like Plato and Aristotle, they said that there has to be a first cause. You can't go back cause and effect forever. It's the whole chicken and egg thing. Eventually, something has to come first. So there has to be a first cause. There has to be a first designer. And Occam's razor would just suggest a single designer, not an infinite regress of designers. Maybe you go back 10 times and that's your first designer, but there's no reason to say that. So ultimately, who designed the designer is a tangent. It's not meaningful to the discussion because it's unnecessary to have an explanation for the designer to know a designer exists. You can get into other philosophy and theology to explain the designer, but on a scientific level, you don't need that. You simply need to observe and say, this was designed, therefore a designer must exist. So, from all this, what kind of conclusion can we draw? And obviously, there's a lot more to be said than I've said. Whole books, whole careers have been devoted to these questions. So I've just brought up a few of the issues. But, given this, what can we say? Well, it certainly appears that fine-tuning the universe does exist. Most people are in agreement on that. There are some holdouts, but there are many, many scientists who would agree with that statement. And it does not appear to be by necessity or by chance. Therefore, logically, it would appear that the best explanation is design. And I think that's about all I have to say. Time to wake up.
You have time for,
Oh, yeah, my, sorry.
you have time for a few questions.
Okay, so yeah, sorry, didn't want to take over everyone's time. So I'm not part of this organization. I have to come here for a class, but it was very interesting. And I like what you did. I've also heard that same argument made by atheists in the same way, sort of an ethical argument that because the chances of creating life are so, infinitesimally small that thus we must preserve it. So what I would start with is are you saying that there is a certain amount of determination, because you're using a teleological argument, so there is an end, and we work backwards from the end, right?
Yes.
We come with the equation to get to the end. So from that, do you think that because we're working in that paradigm of basic Western logic, that you're always going to inevitably end up with a zero-sum designer, because you have to have an equation? Because you're ending with the teleological argument.
That sounds reasonable. I think the evidence pretty much leads that way. That you take in the fine-tuning, and if it's not by necessity or design, necessity or chance, the only real option left is simply design.
Okay. And I guess it's going to sound like a baked-out college freshman student here, but why do you feel it's, I asked you said that it doesn't answer the why when you're talking about the entropic argument.
Yeah.
Why does the why matter in this case? Why, this sounds a little redundant, but this argument doesn't necessarily seem to relate to the why matters.
Oh, okay. So why do we care if there's a design?
Well, yeah. Like why does the why, or why does the universe need to be principled in that kind of way within this argument?
Yeah. Why? Okay. So just to make sure I know what you're asking.
Yeah, guys.
You're asking why does it matter if there's a design?
Why does it matter that it matters if we think there's a designer?
Okay.
Yeah, there's one step there too. Yeah.
I would say a lot of that has to do with what you perceive the designer to be. If you perceive the designer to be some impersonal force, it really wouldn't matter. And it becomes a philosophical question, which is interesting in and of itself, but probably not critical of life.
Yeah.
If you perceive the designer to be a personal being, then I think on an individual level, I think that would be a very important question. Then you have a being that created the universe, must have created the universe with a purpose. Probably would appear to have created the universe intended for life for a purpose. Therefore, there's some purpose to us.
Okay.
And I would think that would be something that maybe not everyone, but most people would be interested in.
Okay, I'm following. I come out of a completely different tradition than Christianity and Aristotelian logic, and so I'm taking it from a completely.
I know people you should talk to.
Yeah, I'm coming here through working through like a Zen lens, so I'm working through Indian fourfold logic through this whole thing, and I'm obviously getting different responses because it feels like when you're talking about the necessity of telos, that is sort of, it ends its own argument in a sense. Telos necessarily perpetuates that there has to be something before an end, if there is one, right? You're talking about, let me check my notes, sorry, I don't want to misquote you because I didn't want to do you justice. You mentioned the regression of the designer constantly questioning itself. That, the objection I suppose I would have in that case is that the object is that something has to do something. Verbs can't just exist on their own, and that's just mainly a constraint of English. Like you can't just go eat. It's you don't just say that to people. But so if we're not worrying about who created who, then creation as a process, does it have any merit as itself? Does the necessity of the designer have to design someone? Can regression of creation just be creation, or creating presencing itself in a sense?
So could creation have created itself?
Is creation just creation? It's only creating when we observe it as being creative, creating, sort of Heidegger being time, if you will. This is the closest thing I know to the West that you guys have. So, yeah, creating just as itself first, that before the division of self and other and that stuff. If you don't less on the theological side.
Yeah. If I follow what you're saying, I think the reason I would say that creation just couldn't be responsible for itself is that we see a very ordered creation, a creation that has very specific laws, that has very specific design constraints. And I would think that would have to be the creation of a mind. In the same way that when you see something designed by a person, you say that because this is very orderly and very well fit together, this is a creation of a mind. And so creation cannot create itself because creation cannot have a mind before it itself existed. There has to be something external to creation to create it, and to have the mind to engineer creation to be what it has to be.
Okay, because I mean, again, I'm sorry, I'm taking up too much airtime. Because
And
I
if
think
anyone else wants to jump in, you're more than welcome.
Well,
This would be a
I'd
great
say-
one for group discussion.
Yeah, it would be circular reasoning to say that A causes A to exist because A has to exist prior to do that. So
Yeah.
you can't. So I mean, that would
Well,
clearly be a
that's-
circular argument to say creation created itself.
yeah, that is a circular argument, I'll grant you. But I mean, I guess I'll explain this. Fourfold Indian logic works with, okay, so normally in the West you have A and not A. And if you ever have, one and negative one, they cancel each other out. Like, you could, that's basically the argument. We do argument by negation because arguments can't exist on their own, right? When you're working in different traditions, you have paradoxes that exist contemporaneously, but not as themselves in constant state. So you have something exists, it doesn't exist, it exists and not exist at the same time, and then you negate that paradox of continually existing and not existing.
And I would say which one corresponds more closely to what we actually see in reality.
Well, this corresponding in reality, again, I would say that, if you're talking about Cicero, nature is imprinted on all ideas, or all minds, the idea of God, right? That is, again, coming from the same tradition. I mean, I'm working with completely different texts here, so that's why I'm trying to kind of reach.
So are you saying that you can have A and not A at the same time, in the same way, wouldn't it?
Yes, but that paradox is also negated simultaneously. These are all happening simultaneously.
Regardless of what worldview, the basic laws of logic are the basic laws of logic. It doesn't matter what worldview you have, because A and not A can't be both A.
Well, see, that's sort of.
So they're different.
No, but I mean, that's what I'm saying is that's the Western approach. Is that
Well, I'm trying to understand any.
Oh yeah, no, it's fine. It's like I said, I'm coming from a different place. You guys are too.
Does anybody else have any
Yeah.
other questions?
Yes.
Ravi Zacharias, who comes from that tradition, who's a Christian apologist, says, don't worry, even in India, you look both ways before you cross the street and see the bus or be in the intersection.
Yeah.
By the very fact that you contrast different philosophical systems, you're invoking the law of mutual contradiction by doing that. So it's a self-defeating paradigm.
Well, the self-defeating only comes if you're using argument by negation, too, though. Because, again, in my argument, this argument would only fail, I suppose, if it was negated. Because then it would be, as you say, its own logic system collapses on itself. You're still arguing through logic.
You're
right?
contrasting two different.
You're contrasting two things through
different
logic.
deals, and you're saying this rather than this, and that's the law of mutual contradiction.
Exactly. But the law of the excluded middle and the law of mutual contradiction.
Does anybody else have another question?
Oh, yeah, sorry.
D'Angelo's got one.
Yes.
Well, I like to start by saying I'm not a physicist or philosopher, but to me, when you was going about your argument, it just sounded like to me you said basically the universe happened the way it happened, and we don't know a lot of things about the universe, and therefore God is what it sounded like to me.
Well,
Yes,
so you're
you know.
arguing, are you arguing basically, I'm saying God of the gaps?
I'm saying I'm kind of saying that's what you're innately must be saying, because you didn't give any evidence you didn't give any evidence for God. You just said that there were constant. You did not directly connect them to the evidence for God. So that must be what you're saying.
Ultimately, what I'm saying is, if you look at probabilities, then we have a universe that is either so vastly improbable that it absolutely could not exist, or it's been specifically designed to be that way. So again, when you deal with a lot of these type of physics, quantum mechanics, all that, it all comes down to probabilities. So we're looking at a universe of such insanely improbability that most likely is the result of something creating it to be that way.
See, he's not saying the Judeo-Christian God is the creator. He's not saying, basically, yeah, right. I'm just saying is that you're saying like, well, we'll just throw in God in there. It's just that there is some you gotta think of it in just a cause. Like it's this whole Aristotle's, first cause, essentially. So like that's all that we're saying is that there had to be something that was there first to cause these things because of the probabilities.
I mean, that's not what I'm saying. I'm not necessarily disagreeing. I'm not disagreeing with that has to be a cause for, I think that's a cause for everything that happens. I'm just disagreeing with your assumption because it couldn't be nothing more than an assumption when you yourself admit to not having the knowledge necessary to make certain that what you're saying is true. When I say God, I'm talking about a general God. You don't even have enough to connect to a general God yet because you do not have the knowledge to make that statement. You don't have the knowledge or the evidence to even make that statement.
And that's largely because I'm restricting myself to science here. And you can get into philosophy and laws of probability and things that would go more in detail with that. But all science can never actually say something is 100% true. It's impossible. All you can say is this is by far the best explanation for what we see. And I think that given the numbers involved and what we know about the universe, that a designer is the best explanation. Now, something may come up that completely negate that. That's how science works. But you always have to go with what you know. And sticking to the science, I say what we know points to the fact that the universe is designed. But again, if you want to go into philosophy, you can sort of narrow that down a lot more and maybe nail it in and give some measure of certainty that science itself can't supply.
If you stay in science, as time goes, the universe seems less and less sloppy and seems more and more
Very much so.
So that's the issue. I mean, it actually seems more, the probabilities for it to be any other way get even bigger. They don't. So therefore, it's even harder to say, okay, it's by every definition, it's impossible for the universe to be here on its own, just random. By all definitions of what impossible is, Borel's law and probability and all of that, by all of that. So then we say, okay, we're here. It's mathematically impossible, basically, for us to be here. So how are we here?
Yeah.
That's the question.
I think that's a lot of it. People, and there's a difference in the way scientists treat numbers and sort of general people treat numbers and probabilities, is that a general person might think, well, there's a 1 in a million chance, but there's still that 1 in a million. That's why people spend all that money on the lottery. But a scientist would say, well, you have this 1 in 10 to the 120th possibilities. That is impossible. Mathematically, it's impossible.
I'd like to help you out. From what I understand of scientific logic, it's not that you prove things, it's that you don't disprove things.
Yes, exactly.
Yeah, you don't, it's not a positivism, it hasn't been a rational positivism. You don't prove something is true, you prove that something isn't not true.
Yes, something has to be, in order to be scientific, something has to be falsifiable. Yes, Bruce?
Yeah. It seems like sometimes these arguments like multiverse or whatever that want to be very speculative when evidence is presented within the confines of the universe is an attempt to, like Dembski says, to expand the probabilistic resources to make anything possible. But that's tantamount to saying you can't know anything about anything.
Yeah.
And nobody believes that. Those that would say that, they have a schedule, they have a class schedule, they have a calendar, they're going to buy an airplane ticket from Atlanta to Los Angeles. They don't think by some perturbation of matter they're going to end up in Rio de Janeiro. So nobody lives that way, but it's an attempt to expand probabilistic resources if you get painted in a corner with the kinds of things that you presented.
Although I would like to argue that there are people that do continually believe that, but that it's not. I mean, because the tradition I come from does allow for that to exist, but then that phenomenal, the structuring of a phenomenal world and the sort of automatic working, and this is more philosophy than theology, so I apologize for anyone who's not like super into that, is that you can have an ordered universe, but it's also equally not universe at the same time, and it's that though you can have samsaric, or I guess, human imprinting of reason on a system, that doesn't necessarily make the system reason. It makes the human reasoning of the system reason. And that these can contradict each other consistently.
There's a question back here.
Oh, yeah,
So a lot of your argument seems to
like especially in regards to the idea that the universe came about by chance, is that like you said, speculation has no place in science. So, do you mean to say that one shouldn't just openly question something that they cannot observe?
Oh, no. I mean, speculation is great. Speculation is important, but you can never prove a point of speculation. And speculation should always be a first step into finding evidence for what you speculate about.
But is it not the case that certain people are speculating about what you claim they are, and are doing so with that purpose in mind?
You talk about people speculating against or for?
Basically, people speculating that the universe came about by chance. Maybe they're speculating and they're trying to find ways to prove that.
Yeah, and
So
that's great if they can find ways to prove that. And as we said, science always has to be falsifiable, and we should always be open to people falsifying it. So if someone came along with a way of showing that the universe could only have come about by chance, then we'd have to change our minds. And I'm sure people are working on that. But from what I know, from what we know now, I think the far better explanation is that it's not by chance. But certainly speculation is important. People should always be able to speculate the question.
You mentioned people like Penrose and others that are apparently atheists or agnostics or something, but they believe in the fine tuning. They believe the chances are just astronomical that it could have become like this. Do they just go with one of these theories that you falsified toward the end, or do they just say, hey, I'm just agnostic as to how it happened, I'm just saying it sure looks like somebody
Some take that
with it?
approach. Some of them, there are people like, I don't know if you've heard of Thomas Nagel, who came out with Mind and Cosmos recently. He was working more from a biological standpoint, but his logic was that, the standard explanations don't apply, but I don't believe in the God, so there must be some third way. And he wasn't sure what the third way was, we believed it was there. A lot of them seem to take that approach. Some of them just basically don't deal with it one way or another. Obviously, I can't look into their hearts and say what their motives are, and some of them will just say, well, it has to be by chance because there's no other explanation. And because they reject the whole design argument out of hand. But, you have to, I'm not sure what a lot of them, how a lot of them deal with it themselves. A lot of them just seem to say it appears to be there, but I don't believe it. And they don't necessarily go into a lot of detail why.
I was going to say, like, when you say true science doesn't try to prove anything, don't try to disprove anything. It just tries to explain what
Well, no, science tries to disprove.
But this is what I'm trying to say. But I got what you say about this topic is like, is there evidence for God? And by your own explanation, you have not provided evidence for God in the universe. You just provided speculation of what you believe to be evidence.
Well, I'd say, the whole probabilities are evidence. In science, you look at something, and if something's vastly improbable, you say that would be evidence against it. It's not going to happen. Like, scientifically speaking, it is perfectly theoretically possible for an entire human to pop out of existence right here. A completely new person just pops into existence out of sheer randomness. But the numbers against it are so high that it's impossible. We know it's not going to happen.
But you have a...
So I just wanted to ask, what would your response be to somebody like Richard Dawkins, who frequently states that yes, there's a immense appearance of design of the universe and of living things, but then he says, well, it's all because of natural selection and of evolution and of all this sort of stuff that would he almost he says that there's no explanation for physics in the sense that we have the explanation for biology of Darwinism, but that we should just pull out hope for that sort of explanation for physics. Like, would you say that?
I think Dawkins shows a lot of faith.
Yeah.
And there are lots of people who would argue against the natural selection. Obviously, I'm not a biologist, and people who could come in and talk about
I'm
that.
just wondering,
But-
if, like, do they have any arguments that there's almost like a universe cosmos evolution almost?
No,
like, you know-
usually, almost universally nowadays, they revert to the multiverse.
Oh, okay.
That is the preferred sort of get out of jail free
Yeah,
card.
because it would seem like if they're going to look for a similar explanation, like Darwinism, that they would first look to say, well, maybe like certain planets just became kind of morphed into better planets, into better planets, into better planets, and then
Well,
you
to
ever
some extent that is
something
happening.
like that.
There's what's called cosmological evolution, which
Yeah.
it has the same name, but it's a completely different thing from biological evolution.
Huh.
And stars and planets do develop, but but again, it's a very different process, and it's governed by very rigid scientific rules, and you can predict the outcome in a lot of ways where you can't predict the outcome of biological evolution. But even that doesn't explain the initial conditions.
Right.
It's the initial conditions that set it up so that cosmological evolution can take place and produce a universe of life.
Right.
For me, I'm just going to be honest. Even if the multiverse was correct, even if it was correct, and we are just completely random, it still wouldn't answer the question of where did the multiverse come from. I mean, there has to be a beginning.
Yeah, and that's been written a lot about there. Even a multiverse has to have a beginning.
I mean, it doesn't help me. I mean, it just doesn't help me.
It removes the problem one step.
And for me, see, I can picture in my mind me sitting on the edge of the universe, surfing it as it expands, right? But at the same time, I can't fathom in my mind a beginning of a multiverse without a beginning of a multiverse.
Yeah.
I just can't imagine that.
Does anybody have a question?
But anyway, I'm sorry.
Oh, it's fine.
Oh.
Stephen Hawking's idea of the cone instead of the
Yeah.
point, does that
Doesn't
really
do
solve anything, or does it still have to have a
All
beginning?
it needs is that the beginning is not a singularity, but it doesn't remove the necessity of the beginning. Now, taking out the singularity does solve some issues with things like quantum gravity that we don't understand, but it doesn't negate the idea of the beginning. You still have, it's the whole light cone thing, where instead of a sharp point, you now have a curve, but it still terminates.
Okay.
There's still a beginning. It's just not a singularity now. It's this, object with some size. But yeah, that in no way negates the necessity of the beginning at all.
I'm trying to ask multiverse, like, is that literally is literally the only reason they posit a multiverse is because of the fine tuning here? Well, from style change, it just has to be the multiverse, or do they have something a little bit more
String theory,
in depth?
string theory and M theory allow for it. But the problem with string theory and M theory is that they allow for almost everything. They are unfalsifiable. Basically, anything can happen with string theory with the proper setup. So it's allowed for, and so they like to use it, but there's no evidence for it.
So the M theory proves the flying spaghetti monster.
Maybe with one possible solution. But basically, M theory means that any interaction can have any possible outcome. That we see the one we see because we're in the universe where that outcome happens. But that eliminates the possibility of doing science because it makes nothing predictable. It makes nothing deterministic. We just happen to see the results we do because we're in the universe where those results happen. So that's why string theory and M theory are starting to lose popularity. People are beginning to move away from them because they're realizing they just don't work as science.
I think that would be.
Yeah.
Thank you.